Welcome to the deep dive. Today, we're tackling something really cutting edge, PaperBench. Now, in the world of AI, benchmarks are crucial, and PaperBench is a brand new one with a truly, ambitious goal. It's designed to evaluate just how well AI agents can autonomously replicate state-of-the-art AI research papers. Think about that, giving an AI a complex paper and seeing if it can not only grasp the core ideas, but also build the code from scratch and run the experiments to reproduce the findings.
It's a huge leap, really.
Yeah.
I mean, consider that a human expert often needs days, maybe even weeks of intense work to replicate even a single one of these papers.
Right.
That gives you a sense of the immense challenge PaperBench presents to AI.
Absolutely. And the reason behind PaperBench is just as compelling. It's about measuring the true autonomous capabilities of AI agents. This isn't just about, bragging rights.
No, not at all.
It's about understanding how AI can potentially accelerate the progress of machine learning itself. And crucially, studying these abilities with a strong focus on safe development. This ties directly into major AI safety frameworks you might have heard of.
Exactly. Frameworks like OpenAI's Preparedness Framework, Anthropic's Responsible Scaling Policy, and Google DeepMind's Frontier Safety Framework all touch on this need, right? The need to understand autonomous capabilities. PaperBench offers a concrete way to actually measure that specific aspect.
So how does this all actually play out? Imagine AI agents that have the ability to autonomously write and run code.
Okay.
They're given the complete content of a research paper, and their task is basically to replicate the empirical results. This means going through the entire research process, from really understanding the paper's core contributions to building a functional code base from the ground up.
From scratch.
From scratch, yeah, running and monitoring the experiments, and even tackling the inevitable debugging challenges. That's a big part of it, I imagine.
Oh, definitely. And it's not just about getting some result. PaperBench demands complete replication of the reported empirical findings.
Yeah.
That initial understanding of the paper is paramount, followed by developing their own original code base. No peeking at the author's code.
Right, that's key.
Then comes the actual running of the experiments, closely watching the results, and as you said, the often painstaking process of figuring out what went wrong if things don't match up.
Now, where did these research papers actually come from? We're talking about 20 spotlight and oral papers from the very recent 2024 International Conference on Machine Learning, ICML.
Yeah, top-tier stuff.
These are high-impact papers covering a wide range of topics within machine learning, 12 different areas, in fact. Things like deep reinforcement learning, robustness, probabilistic methods.
The whole gamut, pretty much. And to make sure the evaluation is both objective and truly captures the essence of the research, the creators of PaperBench didn't just, wing it with their own criteria.
Yeah.
They developed detailed manual rubrics for each of those 20 papers. These aren't just general guidelines. They meticulously outline every single necessary outcome for a successful replication. We're looking at a total of 8,316 individually gradable outcomes.
8,316. That's a lot of detail. And here's a crucial point. These rubrics weren't created in isolation.
No, definitely not.
They were co-developed directly with the original authors of each ICML paper. So they're accurate and truly reflect what constitutes replication for that specific piece of research. This rigorous process aims to ensure the benchmark truly measures research replication as defined by the original creators, a really key takeaway, I think.
That collaboration with the original authors is absolutely vital. It ensures that the rubrics capture the subtle but important aspects of each paper and focus on evaluating whether the AI truly understood and reproduced the intended contributions.
And it gets even more detailed. These rubrics apparently have a hierarchical structure, almost like a decision tree. This allows them to measure not just a simple pass or fail, but also how much progress an AI makes. So even if an AI doesn't completely nail a replication, it can still get credit for the parts it does successfully reproduce.
That hierarchical breakdown is essential for getting a more nuanced understanding of an agent's capabilities. It lets us pinpoint the specific areas where an AI excels or, struggles, rather than just getting a binary yes-no result.
Now, here's a logistical challenge to wrap your head around. Even with these incredibly detailed rubrics, grading a single replication attempt by a human expert can take, wait for it, tens of hours.
Yeah, that's the bottleneck.
Multiply that by multiple AI attempts across 20 papers, and you've got a massive, massive bottleneck.
Exactly. Manual grading at that scale is simply not practical. This is where a really clever solution comes in. They developed an LLM-based judge to automatically evaluate these replication attempts against those detailed rubrics.
Using AI to grade AI. Makes
Yeah.
sense. And to make sure this AI judge is actually reliable, they created another benchmark called Judge Evil.
Right, Judge Evil.
This was specifically designed to assess the performance of the LLM-based judge by comparing its evaluations to gold standard evaluations provided by human experts.
And the results from Judge Evil were quite promising, actually. The best performing LLM-based judge, using a model called O3 Mini High with some custom scaffolding, achieved an F1 score of 0.83.
0.83. That's pretty good, right?
Yeah, it suggests it's a reasonably accurate stand-in for a human judge, which is critical for making the entire PaperBench initiative scalable. You just couldn't do it otherwise.
Okay, so with this automated grading in place, they put some of the most advanced AI models to the test on PaperBench itself. And the top performer, Claude 3.5 Sonnet, new, using open source scaffolding, achieved an average replication score of 21.0%.
21%.
21%. So you see, while AI is making strides, the ability to autonomously tackle the entire research lifecycle and truly replicate findings at an expert human level, well, there's still a significant gap. This benchmark clearly highlights the current limitations.
That 21% gives us a concrete number to work with. It provides a snapshot of where current AI stands when faced with this very demanding task. And to really put that into perspective, they also established a human baseline for comparison.
Right. They had top PhD students and graduates in machine learning attempt a subset of PaperBench, I think it was 3 papers, with the best of 3 attempts after 48 hours being considered. And they achieved a score of 41.4%. For comparison, another AI model, O1, scored 26.6% on that same subset.
That comparison is really insightful. It clearly shows that while AI is making progress, it's still significantly behind expert humans in this kind of complex, open-ended research replication challenge. About half as good on that subset.
Yeah. They also developed a more streamlined version of PaperBench called PaperBench Code Dev. This version focuses more on just the code development aspect of replication.
Okay, less on the full execution.
Exactly. On this more focused benchmark, that O1 model actually achieved a much higher score of 43.4%.
PaperBench Code Dev appears to offer a more accessible way to evaluate specific aspects of research replication, particularly the coding capabilities. However, the researchers did note that its correlation with the full PaperBench is somewhat weak.
Oh, okay.
So it suggests it might not fully capture the overall complexity of the task. It's maybe a preliminary signal.
Got it. So let's summarize the key contributions of this paperbench.pdf source just to lock it in. First, it introduces PaperBench itself. This benchmark of 20 ML research papers with rubrics approved by the original authors and that crucial automated grading system.
Check.
Second, there's PaperBench Code Dev, the more lightweight version.
Yep.
Third, they gave us Judge Evil, the data set for evaluating the performance of automated judges.
Right, meta-evaluation.
And finally, the paper presents the initial evaluations of those advanced AI models on PaperBench. These contributions together provide a comprehensive framework for evaluating and studying AI's capabilities in autonomously engaging with and replicating complex AI research.
Exactly. These components together create a robust platform for understanding the current state and future progress of AI in autonomously conducting research.
Now, let's dig a bit deeper into the nuts and bolts of how PaperBench actually works. We briefly touched on the task itself, but let's get into the specifics. For each paper in PaperBench, the AI agent receives the paper, naturally, and also something called an addendum. What exactly is in this addendum?
The addendum. It's a really important piece of the puzzle. It contains clarifications provided directly by the original authors of the paper.
Okay.
This helps to resolve any ambiguities or points of confusion in the paper itself, and also clearly defines which specific parts of the paper fall within the scope of the replication task for PaperBench. It sort of sets the boundaries.
Okay, that makes sense. So the AI gets the paper and these author-provided clarifications. What does it actually have to submit to show its attempt at replication?
The submission needs to be a repository containing all the code that would be necessary to reproduce the paper's reported empirical results. And this isn't just a random collection of code files. It's absolutely essential that there's a file named reproduce.exe located at the very root of this repository. Reproduce.exe. Okay. This script acts as the single entry point. It's the command that will be executed to run all the code needed to generate those results.
So if this reproduce.exe script runs successfully and produces the key results reported in the original paper, that's considered a successful replication, right?
Exactly. That reproduce.exe script is the key that unlocks the replication. It needs to be able to, starting from a clean state, regenerate the core empirical findings of the paper.
Now, a really critical point they emphasize is that the AI agents are not shown the rubric during their attempt to replicate.
Right, that's crucial.
They have to figure out what needs to be replicated solely by reading and understanding the paper itself.
That's a fundamental design choice. It prevents the agents from simply trying to, game the evaluation criteria.
Yeah, teach to the test. Yeah.
And instead forces them to truly engage with the research paper's content and identify the most important contributions to reproduce.
And to ensure it's a genuine measure of independent coding and execution abilities, there's a strict rule against the AI agents using or even viewing the original author's code bases. That seems pretty important for the integrity of the benchmark.
Absolutely. The aim isn't to see if an AI can utilize existing code, but rather to determine if it can independently develop the necessary code and execution strategies from scratch, which is a much more demanding test of its understanding and engineering skills.
Okay, so the AI submits its repository with the crucial reproduce.esh script. What happens next? We've talked about grading, but there's an intermediate step called reproduction. What exactly goes on in that phase?
Yes, the reproduction phase. This adds a significant layer of rigor and credibility to the evaluation process. After the AI agent's allotted time for the attempt is over, the submitted repository is copied over to a completely fresh virtual machine.
A clean slate.
Exactly. This VM starts with a clean installation of Ubuntu 24.04 and has access to an NVIDIA A10 GPU. Then, that reproduce.ish script is executed from this completely clean starting point.
So it's almost like a final, unbiased execution in a pristine environment. No leftover files or partially completed experiments from the agent's development process can influence the final outcome.
Precisely. This execution generates all the output files, the resulting data, the plots, whatever empirical evidence the paper reported. It also automatically creates a detailed reproduce.log file, which records every single step and output during the execution of the script.
Okay.
The researchers then refer to this updated submission folder containing all the generated outputs and the log as the executed submission.
And the main purpose of this separate reproduction step is to really ensure that the results are genuinely produced by the agent's code and not just, for example, hard-coded into the submission files. That makes perfect sense for maintaining the integrity of the benchmark.
Exactly. It provides a clear distinction between an agent that can truly implement and execute the research and one that might attempt to take, let's say, less legitimate shortcuts.
All right, now let's dive into the grading process itself. We know there are these detailed rubrics, and they're structured like trees. How does that actually translate into a final overall score for a replication attempt?
Okay, so think of each rubric as that hierarchical breakdown of all the requirements for replicating a specific paper. At the very bottom level of this tree structure are the leaf nodes.
Oh, leaves, correct.
These specify single, very clear criteria that are graded as either pass or fail, essentially, a binary score of 1 or 0. Importantly, every node in this tree, not just the leaves, also has a specific weight assigned to it.
Ah, weights.
Yeah, this weight reflects the relative importance of that particular requirement in the context of the paper's overall contributions.
So once all these individual leaf node requirements are evaluated and given a pass-fail score, how do you combine those into an overall score for the entire replication attempt?
The score for each parent node in the tree is calculated as the weighted average of the scores of its immediate children. This calculation then propagates upwards through the entire tree, from the very detailed leaf nodes all the way to the top, the root node.
Right up to the top.
And the score of this single root node is what they define as the final replication score for that particular submission.
Okay, so it's a comprehensive, weight-adjusted proportion of all the satisfied requirements within the entire rubric. A perfect replication where the AI successfully meets every single leaf node requirement would ultimately receive a replication score of 100%.
That's exactly right. It's a holistic measure that takes into account both how many requirements were met and the relative significance of those requirements to the paper's core contributions.
Now, you mentioned that these leaf nodes, these individual requirements, fall into 3 different requirement types. What are the key distinctions between these types, and how is each one specifically graded?
All right, the 3 types: result match, execution, and code development. Result match nodes are all about assessing whether the executed submission actually demonstrates the replication of a specific quantitative or qualitative result that was reported in the original paper.
Matching the numbers.
Pretty much. To evaluate these, the judge examines the reproduce.ish script the reproduce.log file, and any files that were created or modified during that reproduction step.
Right.
For instance, a specific requirement might be that the F1 score on a particular task should decrease by a certain percentage after a specific term is removed from the model. The judge would look for evidence of this specific change in the output files.
Okay, so that's focused on verifying the final reported outcomes. What about the execution requirement type?
Execution nodes focused on determining whether a particular execution event occurred during the running of the reproduce.sh script. Since perfectly matching the final result match, can be quite challenging, right?
Very hard, yeah.
These execution nodes offer a way to award partial credit for making significant progress towards a result, even if the final numbers don't perfectly align with the paper. These are assessed by looking at the reproduce.sh script, the reproduce.log, and even the source code itself to confirm that a specific part of the intended process, like training a model on a particular data set with specific hyperparameters and recording the resulting scores, actually took place.
So it's about confirming that the necessary computational steps were taken, even if the very final result isn't an exact match. And then we have code development. What does that type of requirement assess?
Code development nodes evaluate whether the AI agent's submitted source code appears to contain a correct implementation of a specific requirement. These can provide partial credit towards fulfilling those execution nodes.
Ah, okay.
For example, an agent might have correctly written the code to generate predictions using a specific model and dataset as described in the paper, but for some reason the reproduce.sh script failed to execute this code correctly.
Happens all the time in research.
Exactly. In that scenario, they can still receive credit for the code development aspect, even if the execution faltered. These are judged by examining the source code itself, along with any accompanying readme files or documentation, and the reproduce.sh script.
So it recognizes that getting the underlying code right is a significant step in itself, even if the actual execution runs into problems. It sounds like having all three of these requirement types provides a much more comprehensive and nuanced way to assess the complexity of research replication.
Exactly. A rubric that consisted solely of result-matched nodes would be ideal in theory, but it's just very difficult for AI agents to achieve consistently at this stage. Including execution and code development allows for crucial incremental progress to be acknowledged and rewarded.
Right.
Conversely, relying solely on code development would make it very challenging to verify the actual correctness of the implementation without seeing it run. So the combination of all three provides a more holistic and robust evaluation.
And just to clarify, the paper includes a helpful table summarizing exactly which files are provided to the judge for each of these requirement types.
Mm-hmm.
For code development, it's the readmes, docs, source code, and reproduce.sh. For execution, it's all of those, plus the reproduce.log. And for result match, it's everything from execution plus the actual output files generated during the reproduction step.
Makes sense. More evidence needed for the higher levels.
And the paper also makes a clear point that if a submission doesn't even include a reproduce.sh script, it automatically scores 0 on all execution and result match nodes. That certainly seems like a strong incentive to get that script working.
It absolutely is. That reproduce.sh script serves as the central point for demonstrating both the ability to execute the code and to ultimately match the reported results. Can't skip it.
Now, to ensure a fair and consistent comparison across different AI agent setups, PaperBench has a defined set of rules. What are the key rules that we should be aware of?
Right, the rules. They're designed to create a level playing field for all participating AI agents. Firstly, agents are explicitly allowed to browse the internet.
Which is realistic.
Very realistic for research. However, there's a crucial blacklist of specific online resources for each individual paper in the benchmark. This blacklist includes the original author's own code repository and any other known online replications of that particular paper.
Right.
Agents that are caught accessing these blacklisted resources face immediate disqualification. Score goes to 0.
That blacklist is absolutely essential to make sure that the agents are genuinely attempting to replicate the research from scratch as intended and not just finding and adapting pre-existing solutions.
Exactly.
Right.
Secondly, there are no strict limitations imposed on the runtime or the amount of computational resources that an agent can utilize during its replication attempt.
Interesting.
However, the researchers strongly encourage those who publish results using PaperBench to transparently report their experimental setups, including the resources they used. This promotes reproducibility and allows for a better understanding of the computational cost involved.
That makes sense. Some research replications might naturally require way more compute than others, and it's important to know that.
Definitely. And thirdly, If a particular experiment described in the research paper relies on accessing external online services, say, using the Hugging Face or OpenAI API, the developers of the AI agent are responsible for providing the necessary API keys.
Okay.
PaperBench isn't designed to test an agent's ability to obtain access to these services, but rather to evaluate its ability to use them effectively if the research requires it.
So the focus is really on the core task of understanding and replicating the research, assuming the necessary tools and services are available. The paper also mentions the use of a post hoc monitor that checks the agent logs for any attempts to access those blacklisted URLs. That sounds like they're taking the no cheating rule very seriously.
They are indeed. This monitor runs after the agent's attempt is completed, and any flagged instances are manually reviewed by the researchers. Across all their initial experiments, a total of 646 individual agent runs, they identify 10 cases where blacklisted resources were accessed.
10 cases out of 646.
Yeah, and those submissions were subsequently disqualified, with their scores being set to 0.
That really highlights both the potential temptation for the AI agents, maybe, and the effectiveness of the monitoring system in catching those violations. Now, we touched on PaperBench code dev earlier. Could you elaborate a bit more on exactly what distinguishes it from the full PaperBench evaluation?
Sure. PaperBench code dev is specifically designed to be a more streamlined and accessible version of the benchmark. The primary difference is that it focuses exclusively on the code development aspect of replicating a research paper.
Just the code.
Right. It completely skips the reproduction phase where the submitted code is actually executed, and the automated judge only evaluates the code development nodes within the detailed rubrics.
So it's essentially assessing whether the AI agent can write the correct code that's needed for the replication without necessarily verifying if that code actually runs and produces the expected empirical results.
Precisely. This simplification offers several advantages. First and foremost, it significantly reduces the need for access to expensive GPU hardware, which is often essential for running the full-scale experiments described in many modern machine learning research papers.
Big plus there.
Definitely. It also leads to substantially lower costs associated with grading the submissions. Using their O3 Mini LLM judge, they estimated that grading a PaperBench code dev submission costs approximately 85% less than grading a full PaperBench submission.
Wow, 85% reduction. That sounds like a much more budget-friendly way to get some form of evaluation. However, the paper does caution that it's a less robust assessment compared to the full PaperBench, right?
Yes, the researchers found that the performance of AI agents on PaperBench code dev has only a relatively weak correlation with their performance on the full PaperBench.
Weak correlation. Okay.
Therefore, while it might provide a preliminary indication of an agent's coding abilities relevant to a research paper, it doesn't fully capture the complexities involved in actually running the experiments and reproducing the reported results. They view it as more of an initial, potentially noisy signal of capability.
Okay, that makes sense. It's a clear trade-off between the accessibility and cost-effectiveness of the evaluation versus the thoroughness and completeness of the assessment. Let's shift our focus to the data set itself. We know it consists of 20 machine learning papers from ICML 2024. What was the process for selecting these specific papers?
The selection process was quite rigorous and systematic, actually. The researchers began with all the spotlight and oral presentation papers from the ICML 2024 conference, and then applied a series of carefully defined filtering criteria.
Filters, okay.
The goal was to ensure that the chosen papers were suitable for the task of autonomous replication by AI agents. Appendix B of the paper provides a comprehensive list of these selection criteria if you want the nitty-gritty.
Could you highlight maybe a few of the key filters they used in this selection process?
Certainly. They excluded papers where the majority of the authors had affiliations that suggested close collaboration would be unlikely due to commercial or geographical reasons.
Interesting. Practical constraint.
Yeah. They also required that each paper contain a substantial empirical experiment that would necessitate non-trivial engineering effort to replicate. This effectively excluded purely theoretical papers or those primarily focused on introducing new software frameworks without significant novel experimental results.
That makes perfect sense. You need something concrete and experimentally driven for an AI agent to attempt to reproduce. Were there any specific criteria related to the computational or data resources needed for replication?
Yes, they specifically excluded papers that required distributed training across multiple compute nodes.
Keep it single machine.
Exactly, to ensure that everything could be realistically reproduced on a single machine, making the benchmark more widely accessible. They also filtered out papers that heavily relied on closed-source pre-trained models or required the collection or annotation of new human data, again, to maintain reproducibility and avoid dependencies on inaccessible resources.
So the core focus was on selecting papers that provided sufficient detail to be replicable primarily from the information within the paper itself, without needing access to external, unavailable resources or requiring new data collection efforts.
Exactly. They also made sure to exclude papers whose primary contribution was just introducing a new software framework, and ensured that all necessary software dependencies were either readily accessible or could be reasonably substituted without fundamentally altering the interesting or reproducible aspects of the research. Following this initial automated filtering, the remaining papers underwent a manual review process, and the researchers ultimately reached out to the original authors, successfully securing collaboration on the rubrics for 20 of these papers. They also utilized 2 additional papers from NeuraPS 2024 workshops as a development set for refining their evaluation methods.
That sounds like a very thorough and thoughtful process to curate a set of relevant and realistically replicable research papers for the benchmark. Now let's return to the rubrics. We understand their critical role in the grading process. Could you walk us through the detailed process of how these rubrics were actually created in close collaboration with the original authors of the selected ICML papers?
Okay, the rubric creation. This was indeed the most time-consuming and labor-intensive aspect of developing PaperBench. For each of the 20 selected papers, the researchers worked directly with at least one of the original authors in a collaborative process that typically spans several weeks per paper.
Weeks per paper? Wow.
Yeah. This process began with 2 research engineers independently drafting an initial version of the rubric based on their detailed understanding of the paper. This initial draft then went through multiple rounds of internal review within the PaperBench research team to refine its structure, clarity, and completeness.
So there was already a significant effort invested in creating a solid foundation for the rubric even before involving the original authors.
Absolutely. Once the internal team felt that the draft rubric was in a reasonably good state, it was formally shared with one of the original authors of the paper under a collaborative agreement.
Okay.
The author then meticulously reviewed the rubric for its accuracy in capturing the paper's core contributions and provided their expert feedback and suggestions. This often involves several iterative rounds of feedback exchange to clarify any ambiguities in the paper's methodology, experimental setup, or reported results.
Back and forth.
A lot of back and forth. Any clarifications that emerged from these discussions were then carefully incorporated into the paper's official addendum, which, as we discussed earlier, is provided to the AI agents along with the paper itself.
Got it.
Finally, the collaborating author had to formally sign off on the final version of the rubric, indicating their agreement that it accurately reflects the requirements for replicating their research.
That sounds like an incredibly collaborative and iterative process, really ensuring that the rubrics were not only technically sound, but also truly captured the intended essence of each paper's unique contributions. And we know these rubrics have a hierarchical tree structure. Could you elaborate on how this specific structure aids in the evaluation of a replication attempt?
Right, the tree structure. It's specifically designed to hierarchically decompose the main outcomes that are necessary to successfully replicate a given research paper. The root node of the tree represents the highest level objective, like the core contributions of the paper have been reproduced.
The big picture.
Exactly. This high-level objective is then broken down into the paper's individual core contributions at the next level of the hierarchy. And those individual contributions are, in turn, further detailed into more granular and specific outcomes, providing concrete criteria that can be evaluated.
Can you give an example?
Sure, the paper provides a good one. A high-level contribution might be fine-tuning a large language model. That could then be broken down into more specific sub-outcomes like GBC2 adaptable cell has been fine-tuned on the specified data set using the exact hyperparameters detailed in section P.1 of the paper. Very specific.
So it's a systematic breakdown of the replication task from the very general down to the extremely specific. And the underlying principle is that if you successfully meet all of these very specific requirements at the lowest level of the leaf nodes, then the higher level requirements that encompass them are also considered to be fulfilled.
Exactly. Therefore, to assess the overall success of a replication attempt by an AI agent, the automated judge primarily focuses on evaluating all of those granular leaf nodes in the rubric. Across all 20 papers in PaperBench, there are, as we said, a staggering total of 8,316 individual leaf nodes.
Over 8,000.
Yeah, Table 2 in the paper summarizes the total number of nodes in each paper's rubric, and Appendix C offers a more detailed breakdown by the different node types we discussed earlier: result match, execution, code def.
And we also know that these individual rubric nodes are assigned different weights. Why is this weighting system important in the overall evaluation?
The weight assigned to each node in the rubric reflects the relative importance of that specific contribution or requirement in the context of the paper's overall significance and findings. It's important to note that the weight is not necessarily directly related to how difficult a particular aspect might be to implement.
Importance, not difficulty.
Right. The weighting system allows the evaluation to appropriately reward AI agents for successfully prioritizing and replicating the more scientifically significant parts of the research.
So it prevents an AI agent from focusing all its efforts on the easier to reproduce but less important aspects of a paper just to achieve a superficially higher overall score on the benchmark. Smart. Now, inevitably, some research papers might have a certain degree of underspecification or ambiguity in their descriptions. How does PaperBench address this inherent challenge?
This is where those carefully curated addendums that we discussed earlier become particularly important. For each of the 20 papers in PaperBench, the researchers manually created a detailed addendum that contained specific clarifications provided directly by the original authors.
The author input again.
Crucial. These addendums are designed to address any ambiguities or potential points of confusion that might exist in the paper's methodology, experimental setup, or reporting of results. They also explicitly state when certain parts of the original paper are considered to be outside the scope of the replication task for the purposes of PaperBench.
Setting clear expectations.
Exactly. In some specific cases, they even created a separate judge-only addendum that contains reference information solely for the automated judge to help it more accurately grade the submissions against the rubric.
So it's a proactive and collaborative approach to try and resolve potential ambiguities and ensure that the AI agents have a clearer and more well-defined target for their replication attempts. Now, we've talked quite a bit about the detailed rubrics and the fact that manual grading is incredibly time-consuming. This brings us back to the LLM judge. Could you explain in more detail why an automated judge is so crucial for PaperBench and how it's actually implemented?
The LLM-based judge is absolutely essential for making PaperBench a scalable and practical benchmark. As we discussed, the sheer amount of time it would take for human experts to manually grade a significant number of replication attempts, potentially tens of hours per paper, makes manual evaluation completely infeasible for any large-scale experimentation.
Just wouldn't work.
Right. To overcome this bottleneck, the researchers developed a relatively straightforward LLM-based judge they've named Simple Judge.
Simple Judge. Okay. And how does the Simple Judge actually go about evaluating a replication attempt against a specific rubric?
For a given submission, the Simple Judge independently evaluates each individual leaf node within the corresponding rubric. For each specific leaf node requirement it needs to assess, the Simple Judge is provided with a carefully constructed prompt.
The prompt matters.
Always. This prompt includes the complete text of the research paper in Markdown format, the entire rubric for that paper represented in JSON, the very specific requirement of the leaf node it is currently evaluating, and the complete submission from the AI agent that is being judged.
That sounds like a significant amount of information to feed into the language model for each evaluation. Is there any concern about potentially exceeding the model's input context window limitations?
That's a very valid concern, yeah. The complete submission from an AI agent, which can often include a substantial amount of generated code, can indeed be too long to fit entirely within the input context window of most current language models.
Right, context windows are always a factor.
To effectively manage this, the researchers implemented a filtering step. When evaluating a particular leaf node requirement, the judge first analyzes the files within the submitted codebase and ranks them based on their estimated relevance to that specific requirement.
Relevance ranking.
Exactly. If the total size of the submission exceeds the model's context window, only the top 10 most relevant files are included in the context provided to the judge for that particular evaluation.
So it's a way of ensuring that the judge has access to the most pertinent information needed to make its decision without being overwhelmed by potentially irrelevant code or files. What's the underlying large language model that they primarily use for this Simple Judge implementation?
Unless they specifically mention otherwise, the primary large language model used as the backend for the simple judge is OpenAI's GPT 3.5 Turbo 16K model, which they often refer to as O3 Mini in the paper.
O3 Mini, okay.
They also provided estimates for the cost of using this model via the OpenAI API for grading. They estimated that it costs around $66 in API credits to fully grade a single PaperBench submission using O3 Mini.
$66 per paper.
Yeah. For the lighter PaperBench code dev submissions, the cost is significantly lower, estimated at around $10 per paper.
That's a substantial difference in cost, really highlighting one of the practical benefits of using the PaperBench code dev variant for quicker and more affordable evaluations. Now, to have confidence in the evaluations provided by this automated judge, the researchers developed Judge Eval. Could you remind us what Judge Eval is and what the key findings were from its use?
Right, Judge Eval. It's a separate, dedicated benchmark that was specifically created to evaluate the accuracy and reliability of automated judges, like Simple Judge, in the context of the PaperBench evaluation framework.
Grading the grader.
Essentially, yes. To construct Judge Eval, the researchers used partial replication attempts of 5 different research papers. 4 of these were drawn from the main PaperBench dataset, and 1 was from their initial development set. These partial replications were meticulously and independently graded by human experts, providing a set of high-quality ground truth labels for each of the leaf nodes in the corresponding rubrics.
So they essentially had a set of examples that were graded by humans, and they could then compare the LLM judges' assessments on those same examples to see how well it aligned with the human experts. What specific metrics did they use to evaluate the performance of these automated judges?
Since the task of grading each leaf node is fundamentally a binary classification problem, the requirement is either met, pass, or not met, fail. They use standard binary classification evaluation metrics.
Like accuracy, precision.
It's exactly accuracy, precision, recall, and perhaps most importantly, the F1 score, which provides a balanced measure of precision and recall. They also used macro averaging to aggregate the performance scores across all of the different papers included in the Judge Eval benchmark.
And what were the key findings and results they obtained from evaluating different LLM models and configurations on the Judge Eval benchmark?
The results, which are presented in Table 3 of the paper, indicated that using the O3 Mini model with their simple judge prompting strategy was the most cost-effective approach that also achieved a reasonably high level of accuracy. This configuration achieved that F1 score of 0.83 at that estimated average cost of $66 per full PaperBench paper.
0.83 F1.
Yeah. These favorable results on Judge Eval provided the researchers with sufficient confidence to use this O3 Mini-based simple judge as their primary evaluation method for the main PaperBench experiments involving the frontier AI models.
An F1 score of 0.83 does suggest a pretty good level of agreement with human expert judges, especially considering the inherent complexity and nuances of evaluating research replication. Now let's delve into the experiments and results section where they actually evaluated those advanced AI models on the PaperBench benchmark itself. What was the standard setup and environment for these experiments?
Okay, the experiments. For all of their main experiments on PaperBench, each AI agent was run within a controlled and isolated environment. A dedicated Ubuntu 24.04 Docker container.
Dockerized.
Yep. This container provided access to a single NVIDIA A10 GPU, which is pretty common in machine learning research. Within this standardized environment, the AI agent was provided with all the necessary information of the research paper in both PDF and Markdown formats, the paper's official addendum containing author clarifications, and a text file containing specific instructions for the replication task. Figure 13 in the paper actually shows what this looks like.
And what about access to external resources? Were the agents completely cut off from the outside world during their attempts?
No, the agents were given access to the internet. This is a crucial aspect, as researchers often need to download software packages, access documentation, or consult online resources during your work.
Right, realistic again.
But, as we discussed earlier, there were strict rules in place, including that blacklist of prohibited websites for each paper, primarily the author's own code repositories and known existing replications. Importantly, the researchers also proactively provided the agents with the necessary API keys and credentials for any relevant online services that might be required by the research papers, like Hugging Face or the OpenAI API.
They even preloaded credit.
Yeah, they even preloaded a certain amount of credit into the OpenAI API accounts to facilitate their use if the paper's research demanded it. smooths the process.
So the agents had the essential information, necessary tools, and internet access, but with specific guardrails in place to ensure they were genuinely attempting independent replication. What was the primary agent architecture or framework that they used for these initial experiments with the frontier models?
For their initial set of experiments, they utilized a relatively simple agent scaffolding called Basic Agent. It's based on the publicly available Basic Agent framework from Inspect AI.
Basic Agent, okay.
This type of agent operates in a continuous tool use loop, meaning it iteratively chooses a tool to use like executing code, browsing the web, reading a file based on its current understanding and goals, and it continues this process until it either decides it has completed the task or it reaches a predefined time limit.
What tools did it have?
They equip this Basic Agent framework with a set of fundamental tools: a Bash shell command execution tool, a Python code execution tool, a web browser tool, and a specialized tool for reading long documents like research papers in a paginated way.
Paginated reader, useful.
Yeah. They also imposed a maximum runtime of 12 hours for each agent's attempt at replicating a paper.
12 hours seems like a significant chunk of time, but considering the complexity of understanding and replicating cutting-edge research, it might still only be enough to scratch the surface, maybe.
That's a good point, and the results sort of bear that out. As detailed in Table 4 of the paper, they evaluated a range of prominent large language models: GPT-4o, O1, which is GPT 3.5 Turbo, O3 Mini, GPT 3.5 Turbo 16K, DeepSeek R1, Claude 3.5 Sonnet New, and Gemini 2.0 Flash.
The big names.
Pretty much. The clear standout performer among these was Claude 3.5 Sonnet, which achieved that average replication score of 21.0% across all the attempted papers.
Still 21%.
Still 21%. Interestingly, OpenAI's O1 model performed significantly weaker, with an average score of only 13.2%. All the other models they tested in this initial round scored below 10% on average.
That 21% average for Claude 3.5 Sonnet is the highest result they observed across all the tested models in that initial setup. While it's still considerably lower than the human baseline of 41.4%, it does suggest, a certain level of capability in tackling these complex research tasks. Did the researchers gain any valuable insights into why the agents performed the way they did by closely examining their detailed logs and behaviors during the experiments?
Yes, they did. After running the experiments, the researchers conducted a thorough manual inspection of the agents' logs to gain a better understanding of their strategies and the challenges they encountered. One notable observation was that most of the models, with the exception of Claude 3.5 Sonnet, frequently chose to terminate their attempts early.
Gave up early.
Kind of. Often claiming that they had either successfully completed the replication or had encountered an insurmountable problem that prevented further progress. This suggested that these agents struggled with effectively strategizing how to utilize the full 12 hours of allocated time.
Didn't know what to do next, maybe.
Possibly. The researchers also specifically noted that the O3 Mini model often exhibited difficulties in effectively using the various tools it was provided with, leading to inefficiencies in its approach. Tool use is hard.
It sounds like effectively managing a long-horizon, multi-step research task like this is still a significant challenge for many current AI models, even if they possess the ability to generate initial plans. The consistent execution of those plans over an extended period seems to be a key sticking point.
That was indeed the primary inference they drew from these initial results. Despite demonstrating some capacity for creating multi-step plans, the models often struggled to consistently take the necessary sequence of actions to successfully execute those plans and achieve the desired outcomes over the entire duration of the 12-hour limit.
Right.
They also suggested that further advancements and refinements in the agentic scaffolding itself, the underlying framework that guides the model's decision-making and actions, could potentially lead to significant improvements in performance on the PaperBench benchmark.
So better agents, better results, potentially.
Potentially. They emphasized that these initial results should not be interpreted as the absolute upper limit of these models' inherent capabilities, but rather as a reflection of their current abilities within the specific experimental setup used.
They also experimented with a slightly different agent framework called iterative agent. How did this framework differ from the basic agent, and what were the key results they observed when using it?
Right, iterative agent. It was specifically designed to address that issue of the AI agents frequently terminating their runs early. It essentially forces the agent to continue running for the entire allotted time limit by removing its ability to autonomously decide to terminate early.
No quitting allowed.
Pretty much.
Yeah.
Additionally, the prompting strategies used with the iterative agent were carefully tuned to encourage the model to work in a more piecemeal and step-by-step fashion, rather than trying to generate and execute a complete solution all at once.
And did this more controlled and iterative approach to execution yield significantly different results on the PaperBench benchmark?
It did indeed. As presented in Table 5 of the paper, the researchers observed a notable boost in the average replication scores for both the O1 and O3 mini models when they used the iterative agent framework compared to the basic agent.
Improvement for those too.
Yeah. However, somewhat surprisingly, the performance of Claude 3.5 Sonnet actually decreased with the iterative agent setup.
Ooh.
Well, it suggests that the specific prompt tuning and forced iteration used in this framework were perhaps better suited to the OpenAI O-series models, and that Claude 3.5 Sonnet might be more sensitive to the particular prompting strategy employed. Prompt sensitivity is a real thing.
Very true.
They even conducted an extended 36-hour run of the O1 model using the iterative agent, saving hourly snapshots of its progress to analyze its performance over a longer duration.
And what were the key findings from that extended 36-hour run of the O1 model with the iterative agent?
They observed a modest further increase in the average replication score for O1 with the extended 36-hour time limit, reaching 26.0%, up from the 24.4% it achieved with the 12-hour limit using the same iterative agent framework.
So more time helped a bit, but maybe diminishing returns.
Seems like it. They also evaluated the performance of O1 with the iterative agent on the more lightweight PaperBench CodeDev benchmark and achieved a score of 43.4%, as shown in Table 6.
That 43.4% on PaperBench CodeDev is a really significant improvement over its performance on the full PaperBench. Again, highlighting the substantial difference in difficulty between just being able to write the necessary code and actually getting that code to run successfully and reproduce the complex empirical results of a research paper. Now, to really provide a crucial point of comparison for these AI results, the researchers established that human baseline performance that we briefly mentioned earlier. Could you elaborate on the design and outcomes of that human evaluation?
Sure, it's a human baseline. To establish this, the researchers recruited 8 participants who were either currently enrolled in or had recently completed a PhD in machine learning.
Real experts.
Real experts. The goal was to have individuals with expert-level knowledge in the field attempt the same kind of research replication task under conditions that were as similar as possible to those faced by the AI agents. Each participant was assigned one of 4 carefully selected papers on the PaperBench dataset and was asked to make up to 3 independent attempts at replicating the key findings of that paper.
3 tries, best one counts.
Exactly. This allowed the researchers to consider the best performance out of the 3 attempts as a measure of expert human capability on that specific paper.
So these were actual machine learning experts tackling the same challenge as the AI agents. What resources and restrictions were in place for these human participants?
The human participants were provided with the same core resources as the AI agents. The research paper, PDF and Markdown, the official addendum with clarifications, and a document outlining the instructions, designed to be as similar as possible to those given to the AI.
Same info?
Yep. They were also provided with access to a single NVIDIA A10 GPU, though in a few cases, due to availability, they had access to an A100 GPU. Similar to the AI agents, the participants were explicitly allowed to use AI-powered coding assistants and language models like ChatGPT and GitHub Copilot to aid their work.
So they could use AI tools too?
Yes. However, they were also subject to the same restrictions regarding blacklisted websites, specifically prohibited from consulting the original author's code repositories or any known existing replications of the assigned paper.
So it was designed to be a fairly level playing field in terms of the core resources and the key restrictions. How long did these human experts typically spend working on their replication attempts?
The participants worked on these replication tasks part-time over a period of 4 weeks. The researchers conducted an initial evaluation of the attempts after the first week, and only the participant who demonstrated the best performance out of the 3 attempts for each of the 4 selected papers was then invited to continue working on the task for the remaining weeks.
Only the best continued.
Right. The researchers also meticulously tracked the active work time spent by each participant using detailed timesheets.
And how did the performance of that extended 36-hour run of the O1 model with the iterative agent compare to the performance of these human experts over time?
Figure 3 in the paper shows this comparison directly. It's quite interesting. One observation was that the O1 AI agent initially outperformed the average human performance in the very early stages of the task.
AI was faster at the start.
Seems so. Likely reflects the AI's ability to quickly process information and start generating code. However, the human experts began to consistently outperform the AI agent after approximately 24 hours of work.
Humans pulled ahead eventually.
Yeah. Notably, the O1 agent's score appeared to plateau relatively quickly after only the first hour of its 36-hour run.
Plateaued after just 1 hour.
Yeah, suggesting that it wasn't able to effectively strategize and iteratively improve its submission over longer periods. In contrast, the human participant scores tended to increase more gradually in the initial hours, maybe as they took more time to deeply understand the paper and plan their approach. But their performance continued to improve steadily over the course of their work.
That's a really fascinating comparison. It highlights that while AI might have an initial burst of activity, the sustained effort, strategic thinking, and ability to learn and adapt over longer durations appear to be crucial strengths of human experts when tackling these complex research replication challenges.
Exactly. It points to a potential fundamental weakness in current AI models for these truly long horizon endeavors that demand sustained problem solving, iterative refinement, and the ability to learn from both successes and failures over an extended period. Something humans are still better at, it seems.
The paper also includes a section briefly discussing related work. What other benchmarks or research efforts in this general area did they highlight, and how does PaperBench differentiate itself?
They mentioned a few. CoreBench, which also looks at reproducibility, but notably provides the agent with the original code repository.
Different premise.
Very different. PaperBench requires replication purely from the paper. They also mention MLE Bench, Emulatant Bench, and DS Bench, which evaluate agents on platforms like Kaggle competitions. They noted these often involve simpler, more established ML challenges compared to the cutting-edge research in PaperBench.
Kaggle versus fresh research.
Right. Another related effort was RBench, which proposes challenging open-ended ML research engineering tasks. They position PaperBench as covering a broader range of subtasks over a potentially longer horizon compared to RBench, and also emphasized the distinction of having a clear rubric-based evaluation in PaperBench versus the more open-ended scoring used in RBench.
And they also briefly touched upon recent advancements in LLMs being used for generating novel research ideas and even solving simplified toy research problems. How does PaperBench relate to these emerging capabilities?
They acknowledge that LLMs are indeed showing increasing promise in areas like generating new research hypotheses and tackling simplified research tasks. But they emphasize that PaperBench focuses on a different but equally important aspect of the research lifecycle, the ability to actually implement, empirically validate, and rigorously reproduce existing state-of-the-art research findings.
Implementation and validation, not just ideation.
Exactly. They also noted prior work using LLMs as judges, but highlighted that PaperBench applies this concept to significantly more complex and demanding tasks than what has been done previously.
It's helpful to see how PaperBench fits into the broader landscape of efforts aimed at evaluating AI capabilities in the context of scientific research. Now, no research project is without its limitations. What did the authors identify as the key limitations of the PaperBench benchmark in its current form?
They acknowledge several limitations. Firstly, the dataset size, 20 research papers. While providing rich rubrics, it could ideally be larger to cover more diversity in ML research.
More papers would be good.
Ideally. However, they did point out that the sheer number of individual requirements within these 20 papers over 8,000 does provide very granular evaluation. Data contamination was another potential concern.
Contamination? How so?
Well, the original author's code for many of these papers might exist online. Future AI models could be pre-trained on this code, potentially leading to inflated scores on PaperBench. They believe current models aren't significantly affected due to the recency of the papers, but it's a future risk.
That's a valid point about the ongoing challenge of potential data contamination as AI models keep training on everything. What other limitations did the researchers highlight?
The demanding nature of the dataset creation, especially the rubric generation, was a big one. It's incredibly labor-intensive, requires deep understanding of each paper, and careful writing.
Hard to scale.
Very hard to scale. They noted the difficulty in training others to create rubrics at their desired quality level. The performance of the LLM-based judge was another limitation. While Simple Judge did well on Judge Eval, 0.83 F1, it's still not as accurate as a human expert and introduces some non-determinism.
Not perfect, yeah.
And finally, cost. Running the agents, especially with GPUs and grading submissions, incurs significant API costs. They estimate around $400 for an O1 iterative agent 12-hour run, plus $66 for grading just one paper attempt. PaperBench Code Dev was partly created to mitigate this by removing the GPU need and lowering grading costs.
So definitely areas for future improvement and further research, both in the benchmark design and the evaluation methods. The paper also briefly mentioned future directions in AI evaluation in Appendix A. What were some of the key ideas and potential avenues for exploration they touched upon there?
They discussed several interesting directions. One was exploring more sophisticated rubric designs, maybe using dependency graphs to better capture relationships between requirements. Another was investigating automated rubric creation, potentially using AI assistance with human oversight.
Automating the hard part.
Exactly. They also considered improving automated judges, the trade-off between specific rubrics and delegating more reasoning to the LLM. And finally, they touched upon the crucial issues of specification gaming.
Gaming the system.
Right, where agents might achieve high scores without genuinely replicating the research, and the potential for adversarial agents designed to exploit evaluation weaknesses.
Those all sound like really important and fascinating areas for future research and development in AI evaluation, especially as we strive to accurately assess increasingly complex and autonomous AI capabilities. The paper also includes several detailed appendices covering aspects like the paper selection process, rubric creation, implementation details of Simple Judge and the Monitor, agent implementations, Judge Evil results, and even an experimental cost reduction approach called pruned rubric grading. It seems like the researchers have been incredibly thorough in documenting their entire process.
Absolutely. The extensive appendices provide a wealth of detailed information for anyone wanting to dig deeper into PaperBench's specifics, understand the design choices, or build upon this work. For example, Appendix shows results broken down by requirement type.
Oh, what did that show?
It revealed that the AI models generally perform better on code development nodes compared to execution and result match nodes. This again suggests a current gap between the model's ability to write relevant code and their ability to actually integrate, test, and run that code successfully to get the desired empirical results.
The execution gap. Makes sense. All right, let's bring it all together for our outro. What are the main conclusions and key takeaways that our listeners should remember from this deep dive into PaperBench?
Well, I think the core finding is that while current advanced AI agents are demonstrating, a growing ability to implement certain aspects of cutting-edge machine learning research papers, they are still quite far from being fully autonomous researchers, capable of end-to-end replication at the level of human experts.
That 21% score.
Exactly. That 21.0% average score for the best agent really highlights the significant complexity of real-world machine learning R&D and the current limitations of AI in tackling these long-horizon multifaceted tasks.
But it's crucial to keep in mind that these are still relatively early results in this rapidly evolving field. And as the researchers themselves emphasize, these findings likely do not represent the ultimate upper limit of AI capabilities in the years to come.
Exactly. Things are moving fast. And the open sourcing of the PaperBench benchmark itself is a really significant contribution to the broader AI research community. It provides a valuable and standardized tool for evaluating, monitoring, and ultimately better understanding the trajectory of AI autonomy, specifically within the domain of machine learning research.
The paper also included a thoughtful impact statement, briefly touching on the immense potential for AI to accelerate scientific discovery, including advancements in AI safety itself, but also acknowledging the potential risks associated with rapid innovation outpacing our understanding and the development of necessary safety measures. They positioned PaperBench as a crucial tool for measuring these rapidly emerging capabilities.
And that leads us to a final thought for you, our listener. Considering the current limitations of even the most advanced AI in fully replicating complex scientific research, and the immense potential impact of AI that could increasingly tackle these kinds of tasks autonomously, what do you believe are the most critical areas for future research?
Yeah, where should the focus be?
Right. Should we be primarily focusing on pushing the boundaries of AI development itself to overcome these limitations? Or should we be equally, if not more, focused on creating even more rigorous and insightful evaluation frameworks like PaperBench to ensure that these powerful capabilities are developed and deployed in a way that leads to beneficial outcomes for humanity as AI takes on increasingly complex research challenges?
Development versus evaluation and safety. It's definitely a crucial question to ponder.